So over the page, we've moved on to part D. It says, when sodium ethanoate is acting as an acidity regulator in food, a buffer solution is set up. This buffer involves sodium ethanoate and ethanoic acid. Explain with the help of an appropriate equation how this buffer solution works when acid is added. Okay, so we've got 3 marks. It's told me I need to add an appropriate equation and that I need to say what happens when acid is added. So let's think an appropriate equation. Well, I can either write out the one for sodium ethanoate and ethanoic acid, or really simply, I can put the HA turns into H plus A minus and give the equilibrium. And then if we say, so what happens when acid is added? So when acid is added, what happens to our position of equilibrium? Well, if we add acid, we're adding H plus. If we add more H plus ions, our Le Chatelier's principle says it's going to counteract that change and move in the opposite direction. So our equilibrium would move to the left-hand side. So when acid is added, the equilibrium position moves to the left. Okay, now what happens to the pH? So the whole point of a buffer is that it minimises the effect of adding that. So minimal change to pH as H plus concentration is effectively constant. And it's able to do this because there's a reservoir. If you remember, we've got a large reservoir, a large reserve of A minus ions from the sodium ethanoate. And there you go, that's your 3 marks. So part E moves on to the final part of the question, which is a little bit more complicated because this is where we get into the buffer calculations. So it says some students investigate buffers involving sodium ethanoate and ethanoic acid. They make a solution containing equal amounts, and this bit's really key, equal amounts of ethanoic acid and sodium ethanoate. Calculate the pH of this solution. And it gives you Ka. Now, you need to remember that, and it's only 1 mark, but let's step back a little bit and remind ourselves of what's going on in buffers. So if we remind ourselves that Ka is equal to H plus times A minus, so products over reactants, HA, and that when we're doing buffer calculations, what we're interested in is the H plus. So if we rearrange this to be our H plus, and we've then got this is equal to, so if we rearrange this, the HA is going to move to the top and the A minus is going to move to the bottom. So we're going to have Ka times HA, so the acid over the salt, the A minus. Now it's told us in the question that we've got equal amounts of ethanoic acid and sodium ethanoate. So we know that they're both so we're going to have the equal concentrations, equal amounts of HA and A minus. So effectively this ratio of HA over A minus becomes 1. So if this and this are equal, we've got 1, this becomes 1, so this gets cancelled out. So we know that our H plus concentration is equal to Ka, which makes this fairly straightforward because I then know that pH is equal to negative log base 10 of my hydrogen ion concentration, which at this point is the same as Ka, so 1.7 times 10 to the minus 5. If I plug this into my calculator, then if I do 1.7 minus 5, and I want to do log to base 10 of that, then I come out with an answer, and remember we're taking the negative of the negative, so this is going to be 4.77. Okay, And then the last question, which is 4 marks, is much, much trickier. So we'll take this one. Okay, move that up. So it says the students then set out to make a buffer solution of a known pH. They have 25 centimetres cubed of a 0.1 molar solution of ethanoic acid. Calculate the mass of sodium ethanoate they need to add to the acid solution to make a solution of pH 5. So if we know we want pH 5, we know that's going to be our hydrogen ion concentration is going to be equal to 10 to the minus 5. So that's how we work out what the hydrogen ion concentration is if we know the pH. We're going to need to say, therefore, that A minus, so we're after the concentration of A minus. So if we look at the equation we used up above, where we said that, where we rearranged our Ka equation, we can now rearrange it to give the A minus concentration being equal to Ka, and then we're going to have times the HA. This time it's going to be over the H plus instead of the A minus, because we've swapped the H plus and the A minus round. So what we need to do is plug in some numbers of what we know. So we know at this point that Ka is 1.7 times 10 to the minus 5. And we know that our HA concentration taken from the question is 0.1. And we know that our hydrogen ion concentration is 10 to the minus 5. So 1 times 10 to the minus 5. So if we plug those numbers in, we get 1.7 5 times 0.1 divided by 1 exponent minus 5. So we end up with an answer of 0.17. So this is equal to 0.17. So this is my concentration of my A minus and what it needs to be. But there's a couple of things. I know that my A minus concentration, that would be for 1 decimetre cubed. I've only got 25 centimetres cubed of it. So I now need to work out how many moles there are in my 25 centimetres cubed. So if I take my concentration, the 0.17, and I times it by my volume, so concentration times volume is going to be equal to moles, so 25 over 1,000, remember, which is the same as dividing by 40, so 1,000 over 25 is 40, so I can either times it by 25 over 1,000 or divide by 40, which you might have seen in the mark scheme, it's the same thing. So if I do 0.17 and divide that by 40, I get 0.0425, and that's how many moles I need of it, but it's asked me in the question for the mass, so I need to quickly work out my MR of CH3COONA. So if I've got 2 carbons, that's 24, plus 3 hydrogens, plus 2 oxygens, plus sodium, which is 23, and tot that all up, 24 plus 3 is 27, plus 32 is 59, plus 23 is 82. So then if I do my number of moles times my mass, so 0.00425 times 82, times 82, I get an answer of 0.3485, so let's round that up, so we're going to get 0.35 grams. Okay, and that's 4 marks.